Okay, in this problem, you're basically told that you have essentially a steady state heat transfer through a slab, and they tell you how much the heat transfer is. They tell you that the heat transfer through the wall is equal to 5,000 watts per meter squared, and the slab is 1 centimeter thick. Okay, this is not to scale. Here's the person that said the temperature on the cold side is 140 degrees C, and there's some temperature on the hot side over here. We're just going to call T. And the question that they're asking you is, gosh, what is the temperature drop if the slab were made of different things? Were it made of, silver, aluminum, steel, ice, yada, yada, yada. And so what we know is that these materials have different conductivity. And since it's steady state, we know that the equation that we're working with is this one here, that the flux of heat is equal to the area negative K times, oh wow, that's really not a K. Okay, there we go. It's negative K times the area times delta T over delta X for steady state. Now, in your book sometimes it says Q equals negative K delta T delta X. The reason I put the area over here is because I see that what they're quoting for Q is watts per meter squared. So I know that the area is actually on watts per meter squared. Is it on this side? Oh, I'm sorry, the area is over there. Let's put the area over there. See my mistakes? So Q over A is equal to 5,000 watts per meter squared equals negative K delta T delta X. And they give you various materials with various Ks, and you're asked essentially to calculate the delta T, knowing that the delta X is 1 centimeter. So let's go ahead and rearrange this, and let's figure out how we might compute the delta T. Okay, I had to swig some Chinese herbs, so nasty. Okay, so let's rearrange this equation over here, and we have Q over A times delta X divided by K is equal to delta T, the absolute value of delta T. All right, so we know that this delta T, if we're calling this the positive X direction, and you say delta T is equal to T final minus T initial, we know that that delta T is going to be, this is lower than that, so this is going to be a negative value. So let's just kind of drop the negative. Let's just, between friends, we'll drop the negative, and we'll calculate this delta T from this relationship, that it's equal to this 5,000 watts per meter squared times the thickness, which is 1 centimeter. 1 centimeter is 10 to the minus 2, 10 to the minus 2 meters, divided by K. All right, we have various values of K. So let's see, what does that get us? That gives us the K value. Okay, let's make sure the units work out. So I'm going to rewrite the delta T here is equal to 5,000 watts. I'm sorry, 5,000 times 10 to the minus 2 is going to be 50. 50. No? Okay, 50 over K, and let's keep track of the units. Watt meters per meter squared. And we know that K is expressed in watts per meter degree C. Okay, so let's look at our units now. Let's do some, possibly crossing out here. We know meters times meters is going to get rid of this meter squared, and the watts is going to drop out here. So we know that, let's see, we've got now this equal to 50 over K degrees C. That's the delta temperature through the wall, if this is a steady state conductivity through this wall. So now we've got these range of delta T's, and so let's just start with one. We know that delta T for silver, delta T silver is equal to 50 over 500 degrees C. which is equal to 1/10 of a degree C. Now, and we can kind of go through each one of these and do the computation. I'm going to be like Julia Child and kind of do this offline and then show you. So I went through all of these and I computed that, as you can see here, for silver, it's about 1/10 or 0.1. Aluminum, 0.25 or 0.3 using one significant figure because we're only given one significant figure. For steel, 0.6 with one significant figure. And these are in degrees C. For ice, 30 degrees C. Spruce, 500, 5,000 for insulation, and 50,000 for aerogel. Again, it depends on the numbers that you pick for K here, but these are sort of ballpark figures using one significant figure. So then the next question is, which of these is unreasonable? So if we go back to our original situation, we know that this is the cold side of the wall. Is it reasonable for silver to be 140 degrees C? Yes. Aluminum is reasonable. Steel is fine. Can ice be 140 degrees C? I don't think so. That would be water. In steady state, can spruce, a tree, can we have 640 degrees C here and 140 here? I don't think so. If this were wood, I think the flame temperature for wood is probably around, I don't know, maybe 300 degrees C, maybe 400 degrees C. And then we have insulation, 5,000 degrees C across this. No, I don't think so. And aerogel, 50,000. Once again, those are also unreasonable numbers.